Good morning, everyone, and welcome to the Tejano Virtual Events Happy Math Hour, your weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carrizales, and Albert Isasi. This session will be recorded so that you may come back to it later. Also, it is recorded so others who may have missed out on today's events will be able to come back and watch it. Thank you very much for attending this great presentation. At this time, please mute your mics for the best sound experience. Otherwise, feedback could interfere with the information that we'll be sharing today. Without any further ado, here is Mr. Albert Isasi. Mr. Ruben Carrizales, sorry.
No worries, no worries.
I wanted to change your class.
Right, yeah, we could change our class. No worries. Um, Everything's all good. Well, welcome everyone. Thank you for joining us again for another of our review of our Happy Math Hour. Um, please hang in there. We're past the halfway mark, okay? So we're almost done. So again, thank you for joining us. Again, any questions you may have on my presentation, please feel free to raise your hand, put it on the chat, so we can discuss it. Okay. So for today's session, we are going to review exponential and logarithmic properties. Okay. Um, and as you've seen in class by now, um, you hopefully you know that exponents and logs, we're covering them at the same time because they're inverses of each other, they're opposites of each other. So we can use this information in order to solve situations like the one we have here. It says solve for x. Okay, so we have a log of base 5 and our input is 125. So as some of us have discovered, if we are using just a scientific calculator, we can't evaluate this log directly because some of our calculators do not have a way to change the base, right? So what we can do is we know that our scientific calculators can solve any exponential function. So that's what I'm going to do. And maybe you have a test question that it's going to involve this. It's going to ask you, having this log equation converted into its equivalent exponential form. And that's what I'm going to do. I'm going to convert this log into its inverse or equivalent exponential form in order for me to solve this. Okay, so let me go ahead and do this. So the way I do this is to change it to exponential equation. I look at the log and I see that this log, its base is 5. So my exponential function also has to have a base of 5. So that's what I'll do. My base of my exponential is base 5. And because they're opposites of each other, this is what I do. The input of the log, which is 125, becomes the output or the answer of the exponential equation, which is 125. And the answer of the log or the output of the log becomes the input or the exponential version of the base 5. So now, if you don't see it right away, what I can do is I can use other properties in order to solve this. What I can do is I can take the 125 and convert it into an exponential number. So I can say that 125 is the same thing as 5 cubed. Now, if you don't know how to do this, the way you can do is you can do a factor tree to get 125 to become 5/3. And the way you do that is you divide this number by the first prime number that is divisible by this number. So since this number ends with 5, I would divide by 5, and I would divide by 5 until I have only prime numbers. So 5 will divide into 125 25 times, and then 25 will divide into 5 another 5 times. So 5 times 5 times 5 gives me 125. So the reason why I did that is now I can use one of my other properties that I also learned from 2.1, excuse me, 3.2, I believe, that we saw that we can use our one-to-one property that says that when I have two equations that have the same base, for this equation to be a true statement, the exponents also have to be the same. So this becomes easy answer. The answer for x has to be 3, right? So again, I can use my information that I know that I can convert this log into its equivalent exponential form to solve any log without actually using a calculator. Okay, so let's go ahead and move on. Um, so how about this one? Have the log of base 2 input 25 is equal to x. All right, so this one might be a little bit challenging, but let's go ahead and do this. It says, let's first change it into its exponential equation. Again, this is my log. My log has a base 2. My input is 25, and I'm trying to solve what is this going to give me. Yes, so let's go ahead and convert it. So since my log had a base 2, my exponent also has to have a base 2. Okay, so the input of the log is the answer of the exponent, or the output of the exponent. And the output of the log, or the answer of the log, is the input, or it's the exponent value of the 2. Now, I had seen already that this one's a little bit difficult to solve because on this particular one, there is no way that I can make 25 into a number that has a base 2. Its only base that it could have would be 5. 5 squared is 25, but I can't make that into a 2. So on this particular problem, we would have to use our calculator to solve this. Okay, so and I'll show you how to solve a problem like this in a second. Okay. So one way that I can do this, and I have some snapshots of two different calculators. Again, for those of you, if you are doing an online class and you're using a graphing calculator, so be it. Okay, so one way you can do it is by evaluating this. But again, if you try to put this, okay, this is not the correct answer. This is what I want to point out to you. Your calculators, you don't see a base here, right? So since you don't see a base, that means that your calculators, especially for those who have only a scientific calculator, like the one on the right, um, it only does logs that are base 10. Okay, it does not do logs of base 5. Now, for instance, on this Casio one, it does allow me to change the base. Okay, so it does let me do a base 5. The one on the right, the one on the left, even though it's a graphing calculator, again, it doesn't have a way to change the base. It only does base 10. Okay, so when I evaluate, if I'm using a calculator that allows me to change the base, okay, if I allow the base 5, my answer is this answer here. Okay. Now, what if you don't have a calculator that allows you to change the base because you are just using a basic scientific calculator? Well, there is a way to change the base of a log, and these are the ways we can change it. Okay, so for instance, there's three different ways to change it. So one of them is if I have a log of base a of input x, the way I change the base by using a calculator that only does base 10 is by doing this. The log of base 10 of x, the input, divided by the log of base 10 of the base of the log. Okay, that would allow me to do my calculation again because my calculator does logs of base 10. Um, so the other way you can see it is just by doing the log of x divided by the log of a. Or on this one, what I can do is I can use my natural logs. All scientific calculators have a natural log button, and the way you can bypass the base is by doing the natural log of x, the input, divided by the natural log of the base that it's given, okay, a. So these are ways that I can use my calculator to solve that previous problem. Now, this is not the only way. We can also use our inverse properties, which I will also show you in a minute. Okay. All right. So let's look at these problems here. Evaluate the logarithms using the change of base formula. Round your answer to 3 decimal places. Okay. So on these problems, I'm practicing just the formulas that I just showed you. Okay. So let's go ahead and do the A. So for the A, let's say that I have a calculator that only does base 10, okay? So the way I would solve the log of base 3, input 11, since my calculator only does logs of base 10, I would do the log of base 10 of 11 divided by the log of base 10 of 3. And again, I don't have to put the base with because my calculator only does base 10. When I do the division of these two logs, it's going to give me my answer. And again, I'm rounding to 3 decimal places. So again, just a little quick review on how to round is since it said 3 decimal places, so I look at 3 numbers after the decimal period, and then I look at the fourth place. If that number is 5 or larger, that third decimal place is going to go up one. But if that fourth number was less than 5, meaning it was 1, 2, 3, 4, or even 0, then the number stays the same. So in this particular problem, an example, since the fourth number after the decimal place was a 6, this 2 becomes a 3. Okay, so this is how I round. All right, let's look at a B. Now B is giving me that my base is pi. Now pi is a symbol, and pi is represented is a symbol that represents a number. It's 3.14, and it's a number that keeps repeating. But again, our calculators can solve these problems. Okay, so again, all I have to do is put the log of base 10 of 0.5 divided by the log, and I put my symbol pi. My calculator will evaluate that pi symbol to the number. And when it does the division, again, I get a negative number. And again, and since I'm rounding to 3 decimal places, again, my calculator, I'm going to need to look at the fifth place. The fifth number is 5. Since that number is 5 or larger, my 5 on the third place is going to go up one. So my answer is negative 6.06. Yes? So this is a way I can bypass something that has a base other than 10, and we call this the change of base formula. Okay. All right. Now let's review some of our properties of logs, which will also allow us to solve these same examples without having to do change of base. Okay. So, and it's crucial that we know our properties to do other things with our log equations. Okay. So what I always like to do is I always like to review both exponential and logs, but for right now, I'm just gonna do the exponentials because this is the ones that most students forget. Okay, so the first property, the one of the most important ones that is very similar to my exponential, because if you see I have my exponential references on the right. Okay, um, when I put in a value for one for a log, it doesn't matter what the base is, whatever the base is, the answer will always be 0. Okay. Similarly, as my exponential. Okay. My exponential, any any base, when I evaluate it to the 0 power, the answer will always be 1. Okay. Again, these guys are opposites of each other. On 1, the input is 1, my output is 0. Here, my input is 0, my output is 1. Okay. They're inverses of each other, and they always work this way. All right. So then the second one is it's called our identity property, that it says that when I have a log of base A and I input that same value, my answer will always be 1. Similarly to my exponential identity property, we never write a 1 on top of a number because we always know that it's only one number. We don't have to tell you that there's one. So we just write A. We already know that there's only one A. But we write this A to the 1 is our identity property for exponents. That says that if I have one exponent, that means I only have one A. All right. So let's look at our third property. Our third property, it's sometimes called the inverse property, or it's also part of our power property, that it says that when you have a log of base A to some base A to some exponent, you're going to multiply the exponent, or in this case, because it's the identity property, a with a base a, that becomes 1, and 1 times x is just the x. So you can call it also the inverse property. You see it better with the law, with the exponents. If I have a base a and I take it to the exponent of a log that has the same base a, the answer is going to be x. Okay, so a lot of students like to say that these guys cancel. When you have a log of base a to an input a, you only get the x, right? These cancel, but it doesn't cancel. They just becomes 1. Okay, similarly, oppositely, have a base a with an exponent of a log of base a with a cancels, giving you just the x. Okay, so again, the book calls this the inverse property. And then one of the most important and probably the most used properties that we will use a lot to solve logarithmic equations is this last one, which is called our one-to-one property. And our one-to-one property, hopefully it's very easy to understand. that it says that if I have a log of a base A with an input x, and I have it's equal to another log that has a base and another input. The only way that I have a true statement with these two is that the logs have to have the same base and to have the same input. And it only makes sense that it has to have the same base and the same value evaluated for them to be equal to each other, right? Or to have a true statement. And also similarly, we have a one-to-one for exponents, that it says that for these two equations to be right, for x be equal to y, then that means that the base has to be the same, that x has to be the same value as y for this to be a true statement. And again, to better see any of these properties in play is to see examples. So let's dive in. But before we can get to see these properties, let's practice evaluating the properties by this homework problem. I get this question a lot in the homework, and let me show you how to solve this. Okay, it says use the properties of logs to write the logarithmic in terms of log base 5 of 2 and log base 5 of 3. All right, so I look at this log of base 5 of 6. Okay, and what I'm going to do is I'm going to use my product rule for properties, and I put my properties down here. Okay, some other fundamental properties of logs, and my product rule says this. I'll tell you that if I have a log of a base and I have two things that are being multiplied inside to evaluate that log, I can expand it or use the product rule to have two logs by doing addition. So let me show you. The first thing that I would do is I would convert the 6 into 2 times 3. 2 times 3 is equal to 6. Now I have the product visually. I have a log of base 5 that inside two things are being multiplied. So my product rule says this. I can expand this or put it into two different logs. The log of base 5 of 2 plus the log of base 5 of 3. Now, what I like to tell my students, the way to fully understand this is most of my students understand exponents. Like for instance, if I ask my students, what is x squared times x cubed? Well, the answer is x to the 5. All you had to do was add the exponents. That's the product rule for exponents. I had uh, I had two exponents with bases, and I added the exponents to get one base. Here I have one base, and I'm going to two bases. See, they're opposites of each other. Okay, so again, um, so this is all I had to do. The problem asked me to rewrite log of base 5 of 6 into a log that had a base 5 of 2 and a log of base 5 that have a base 3. And here you go. That's all I had to do. Okay. All right. So let's look at another example. Okay. And this one says find the exact value of the logarithmic expression without using a calculator. Okay. Now, most students are going to get this problem wrong because they'll use their calculator and give an estimation answer. They're going to give a decimal value, and WebAssign will count it wrong. It'll know that you're using your calculator. Okay. They want you to rewrite this using your properties of logs. So, for instance, I have the log of base 4 of the cube root of 4. So what I want to do is I want to rewrite the cube root as an exponent, as a power. So that the cube root of of any number is written as an exponent as 1/3. Okay, so I have here the log of base 4 of 1/3. So now I'm going to use my power rule, and my power rule says that when I have an exponent to a log, I'm going to multiply that exponent to the log. So this is going to give me um, 1/3 times the log of base 4 of 4. Oh, but now I can use my identity property, right? That says that when I have a log of base 4 of input 4, what is my answer? My answer is 1, right? So I have 1 times 1/3, and I simplify, my answer is 1/3. So I was able to solve this somewhat looking complicated problem um, and have the exact answer. It's a fraction without using a calculator, okay? And all I'm doing is using my properties. All right, so let's practice some more of these. Finding the exact values without using a calculator. Okay, now let's do one with a natural log. So I have the natural log of the fourth root of e to the third. Okay, so the very similar process. The first thing that I need to do is I need to write the fourth root as an exponent. Okay, so the fourth root, that's just 1 over 4. Okay, and then I have e cubed. Now on this one, I have to apply my power rule that says that when you have an exponent to another exponent, this is the power rule for exponents now, is that I'm going to multiply the exponents. So then I have natural log of e to the 3/4 power. Then I use my power rule that that says that when I have an exponent to another log, I'm going to multiply the exponent to the log. So I have 3/4 times natural log of e. And then this one is also the inverse property for the logs, the ones that we covered, that says that if I have a log to its inverse exponent, that's going to become 1. So 1 times 3/4, my answer is 3/4. Easy stuff, I hope. Okay. All right. Let's look at the second one. The second one will require us, or B is going to require us to do a little bit extra work. So I see that I have two logs. So what I'm going to do first is apply my power rule because I have two logs that have exponents. So the first thing that I'm going to do is I'm going to simplify by canceling out those exponents. And the power rule says that I'm going to multiply this exponent to the logs. So then that's going to give me 4 times the natural log of e plus 8 times the natural log of e. And oh, now again, I have the inverse property. Natural log of e is the inverse of each other, so that becomes 1. So then I have 4 times 1, 8 times 1. Again, it's the same one that I had before. And then now this becomes just algebraic, easy problem. 4 plus 8 equals 12. And again, I'm doing all of this without having to use a calculator just because I know my properties for logs. Okay. All right, let's look at this one. Use properties of logs to expand the expression as a sum and difference and or constant multiples of logs. All right, so basically what this example is asking me to do, I have a single log and it wants me to expand it to multiple logs. And the way I'm going to do this is precisely by using my properties of logs. Okay, so let's go and do it. So the first thing that I see is that I have an exponent being applied to this log. So I'm going to apply my product rule. Then I'm going to take that exponent and I'm going to multiply it to the log. Okay, so um, sorry, I'm getting ahead of myself. Excuse me. The first thing that I'm going to do is I'm going to do my my product rule, which is that I have two things. I didn't see the z there. Okay, do you see that I have a z times a z minus 1 to the fourth? I'm going to apply my product rule, and that says that when I have two things that are being multiplied to a log, I can expand it by the addition of the two logs. Yes? So then I have the natural log of z plus the natural log of z minus 1 to the fourth. Okay, now I'm going to apply the power rule. Okay, so now apply my power rule. This first one, I can say that it has a 1, so 1 times the natural log of z is just the natural log of z. So I don't have to worry about the power rule for the first one. But this one does have an exponent, like I had mentioned. I have an exponent of a 4. So I need to multiply that 4 to my log. Okay, so it's going to give me the second line, natural log of z times 4 times natural log of z minus 1. Okay, now, can I do anything else? No. So here, oops, this is my final answer. Okay, I expanded it. I went from one log to multiple logs. In this case, it was just two. And then the fact that it says that multiples, that's that power rule. It says it doesn't want any exponents. That's what multiple means. That all of your exponents have to be of exponent of 1. Okay. All right. So let's do my favorite one. Okay, I love this one. So I have this log of base 5 of the square root of x squared minus 9 divided by 4. Okay, now on on this one, um, this value here, a has to be greater than 3, has to deal with the issue with the numerator with the root, because if 3 was if x was 3, Okay, 3 squared is 9, and 9 minus 9 is going to give me 0. 0 divided by something is just going to give me 0. So this is just telling you that we're going to get an answer, and A is never going to be 3 because then we would get an answer of 0. So that's all this right side is saying. Okay, has nothing to do with us doing our work. It's just a safeguard. Okay, all right. So let's go ahead and do this. Let's attack this problem. I have a log of base 5, and if I see inside this log, what's happening is I have two things that are being divided with each other. So what I'm going to do is I'm going to apply my quotient rule. My quotient rule says that when I have two things that are being divided to a single log, I can expand it by subtracting the numerator by the denominator. So here I have the log of base 5 of the numerator, the square root of x squared minus 9, minus the log of base 5 of the denominator, which is 4. Okay? All right, but now I'm not done. Just like my previous examples, I can convert the square root into an exponent value. That exponent can be written as 1/2, right? So now I have the log of base 5 of x squared minus 9 to the 1/2 minus the log of base 5 of 4. Okay, all right, so now I apply my power rule, and my power rule says that I'm going to multiply that exponent, and I have 1/2 a log of base 5 of x squared minus 9. Now here, most of my students will stop and give me this answer, and this answer would be wrong. I am not done, because inside here, this number in here can still be simplified or reduce. If you see here, what I have here is a difference of squares. I have x squared minus 3 squared. 3 squared is 9. So what I can do is I can simplify or factor that input value there, that x squared minus 9, that can be factored or simplified times x minus 3 times x plus 3. So if you see here, now I have a log of base 5, and what's happening in here? Have two things that are being multiplied with each other. So now I'm going to apply my product rule again. That says that when I have two things that are being multiplied inside, I can expand by the addition. Now don't forget the 1/2. I have to carry the 1/2 to the expansion. So my answer, my final answer now is going to be 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3 minus log of base 5 of 4. So if you see, I expanded a single log to multiple logs. This one expanded to 3 different logs, all with a power of 1. None of them have exponents. Now the 4 can be written as 2 over 2, but um, I can't apply the power rule, or so, the homework will accept this as a 4. Okay? Now be careful on some. All right, so let's do two more. Okay, use properties of logs to expand. All right, so let's go ahead and do A. I have a log of base A, and my input here is a division. So since I have two things that are being divided with each other, I'm going to apply my quotient rule. It's going to separate to two logs. The log of base 8 of the numerator, which is x cubed, minus the log of base 8 of the denominator, which is y cubed z to the fourth. All right, now I see that both of these two logs have power rules that I can apply. So I'm going to apply, well, okay, we'll do it separately first for the second one. I'm going to apply my product rule for the second part. Okay, I'm gonna separate these two. Okay, so I'm going to have the log of base x cubed, and this is one of the reasons why we wanted to separate this, because I have a subtraction here and other stuff is going on here. Don't forget to put up parentheses here. Okay, so I'm going to put up parentheses and apply the product rule to only this part here. So I have two things that are being multiplied to a single log of base 8. So this simplifies to the log of base 8 of y cubed plus the log of 8 base 8z to the fourth. Okay, now I can apply um, my power rule, or let's simplify some more again. I'm gonna go ahead before I apply my power rule. Again, the order doesn't matter, but I'm just following this order that's given to me. I'm gonna distribute the negative, okay? And I'm gonna do negative times the log of base 8y cubed is negative log of base 8y cubed, and negative times a positive is a negative, okay? So again, now I've simplified. And now go ahead and use my power rule, multiply those exponents, and I have my final answer. 3 log of base 8 of z minus 3 log of base y minus 4 log of base 8 of z. Okay? All right, let's do B, one more. All right, so first we have to, again, rewrite the 10th root. That 10th root of that natural log can be written as 1 to the 10th power. Now, this is a word of caution, okay? Most of my students miss this problem because they forget to put parentheses on this whole thing, okay? Don't forget the parentheses or be mindful of your parentheses, okay? All right, so now that I have that, I have inside here, I see that two things that are being multiplied with each other. So now I'm going to apply the well, first the product rule. Again, the order doesn't matter, but I'm going to apply the product rule first, okay? And I'm going to do 1/10 natural log of this that's inside. Again, I have a product rule inside. I'm going to go ahead and apply it. So I have 1/2 natural log. Again, I could have done it at the end, like I said, because I'm going to keep my parentheses. Natural log of x to the 7th plus natural log of this guy here. Okay, now this one in here can be simplified, but this one can be simplified. This has a power rule inside here too. So let me go ahead and, well, let me distribute first. I have 1/10 natural log of x to the 7th plus 1/10 natural log of x plus 5 to the 7th. I'm going to apply the power rule to the 7th. Again, I could have done it first or last. So my final answer is 7/10 natural log of x plus 1/10 natural log of x to the 5th plus 7. This one again cannot be simplified. I'll just leave it alone. Okay. All right, now let's do it backwards. Your homework problem says condense the expression to a single quantity or a single log. So again, I'm going to use my properties of logs to do the very exact same thing, but backwards. Okay, so let's do this. Okay, so on this one thing that I can do is for the numbers in the front, since this is a number that is being multiplied to the log, that comes from the power rule. So that means that this number that was being multiplied is an exponent. So I'm gonna put it back as an exponent. Okay, this 9 is really to the 9th power. Okay, now be careful. The subtraction is just a subtraction for logs. It doesn't mean -9. So don't put -9 exponent. That's not what that means. Okay, and on your homework, it tells you, it specifies, it says, be careful. The subtractions are not negative exponents. It does warn you and tell you. Okay. All right, so I have to follow an order of operation on these. Okay, so I did my exponent first. Now I have two things that are being subtracted with each other. So I can use my quotient rule that says when I have two logs that are being subtracted, this came from a division of a numerator and denominator. So the first one is my numerator, which is 3x. My second one is my denominator, which is x to the 9th. And this is my final answer. I went from two logs to a single log, log of base 6 of 3x divided by x to the 9. Okay. All right. We can simplify. So we can simplify the x's. So let's do that. We want to always simplify. So I have an x to the 1 on the top, x to the 9th on the bottom. I'm going to apply my exponent rule for bases that I have. When I have two bases that have the same base that are being divided, I'm going to subtract the exponents. So 1 minus 9 is a -9, but that's a negative exponent. Sorry, 1 minus 9 is 8, -8, but -8 on the top becomes an 8 on the bottom. So this is 3x to the 8th power. Okay. All right, let's do some more of condensing. So let's do A and B here. So let's do this first one. The log of base x minus 6 log of y plus 7 log of z. So again, we have to follow an order of operations. So my first thing that I have to do is deal with my exponents, okay? Power rule. Those numbers that are being multiplied to the logs are exponents. So I have, this one only had a 1, so I don't have to worry about that, but this is a 6. This becomes y to the 6. This one's a 7. This becomes z to the 7th. Okay. All right. So now let's just do our properties. So we like to do things like the way we read books. We like to read from left to right. So that's how we like to combine. Since addition and subtraction have the um, same level of work. It doesn't matter who I do. Again, the way you do these orders, as long as you follow the steps, the order doesn't matter. Okay, and the preference it varies from instructor to instructor. So on this one, I'm just gonna go from left to right. So the first thing that I'm gonna do here is the subtraction of the log of base 10. Again, this is a base 10 since they didn't write it. I know it's a base 10, so log of base 10 of x minus the log of base 10 of y6 can combine by doing my quotient property, the log of base 10 of x to the y to the 6. Now again, I didn't mention this, but I can only use my properties if I'm dealing with the same base. Like for instance, if they would have given me log of base 9 minus a log of base 10 plus the log of base 6 for these, I cannot apply any of the properties to my answers like that. I cannot combine like terms. They're not like terms. I can only do this if my bases are the same base, okay? All right, so I combined those two to this quotient property. Now you see that I have just two logs and they're being added. This is the product property or product rule that when I have two logs at the same base, I am going to multiply the inputs. So I'm going to multiply x over y to the 6 times z to the 7. Let's simplify by multiplying those two fractions together. So this gives me the log of base 10 of x times z to the 7th divided by y to the 6th. Okay? All right, let's do the next one. Let's condense this um, long equation. So on this particular problem, they are giving us the order of operations. Do you see that they put brackets on this one? So what they're telling me is that they want me to do this first, okay? So since they want me to do this first, this is a product rule. It says that I have the natural log of x plus 1 plus the natural log of x minus 1. I have to do this first. Product rule says that I multiply these two logs to a single log. I have the natural log of x plus 1 times x minus 1. Okay, all right. So now I can simplify. I know that this is a difference of squares, or if you FOIL it out, okay, x times x, the x times 1, the 1 times x, and the 1 times a minus 1 gives you this. But I know that this is going to give me x squared minus 1. So difference of squares. Okay, so now you see that I have only two logs that are being subtracted with each other. I can use my quotient rule, and my quotient rule says that when I have two logs that are being subtracted by each other, this becomes a division, right, or a subtraction, or the division of the numerator of x. The first one is the numerator divided by the second one, which is the minus 1, and voila, I have my answer. This is my final answer. I went from 3 logs to only 1 log. Okay. All right, let's now use some of our properties to solve for logs, okay? Um, so let's go ahead and do this first one. 2x is equal to 4. So this is very similar to the one that we had at the beginning where we said, I can't um, get bases, but for instance, with this one, I can do what I apply my one-to-one property by doing this. I can convert this 4 into a base of 2. Okay, so if we see here, 2 squared is 4. To answer this one for x, this one was an exponent. For these two exponents to be equal to each other, I know that this x has to be 2. Okay, so this is my one-to-one property. All right, so how about this one? To solve for this one, what I'm going to do first is I'm going to add the natural log of 13 on both sides. That way I can get, or I can use my one-to-one property. And by doing this, by adding that natural log of 13 on both sides, I have the natural log of x is equal to the natural log of 13. This one becomes a super easy problem. That for this to be a true statement, or again, I'm using my one-to-one property, that for these two logs to be equal to each other, x has to be 13. It can't be any other number other than 13 for it to be a true statement. Yes? So this is x equals 13. Okay? So let's look at C. Okay? e to the x is equal to 13. So what I'm going to do is I'm going to use my inverse property to solve for this one. And what I'm going to do is I'm going to multiply the natural log of both sides. So when I multiply the natural log of both sides, natural log of e to the x times the natural log of 13 will allow me to use two properties on the left. Okay, so the left, I can use what's called my power property or inverse property for logs, that this one will be x times the natural log of x times the natural log of e, but I know that the natural log of e is just 1, so this is x times the natural log of 13. Now all I have to do is use my calculator to evaluate this value, because my calculator has a natural log button. It's a log of base 10. So when I put it into my calculator, and again, in this particular problem, it asks us to probably round to 3 decimal places. So my calculator gave me 0.5649. That fourth value was larger than 9, so the 4 became a 5. Okay? All right. So let's solve this for this one. Solve this exponential problem algebraically, and then says to round our answer to 3 decimal places. So this is a problem that requires a two-step process. Okay? The first is algebraically. All right, so to solve for this one, this is I can use my one-to-one property to solve for this problem. It says that, and again, my one-to-one property says for these two exponents to be equal to each other, the exponents have to be equal to each other. So since they both have the same base, I can set the exponents equal to each other. So x has to be equal to x squared minus 6. So since I see that I have a x to the second power, I have a quadratic equation. So in order to solve this quadratic equation, I'm going to move everything to one side. Okay, so I have 0 is equal to x squared minus x minus 6. So again, under our belts, we have a lot of methods to solve quadratics. We can use our quadratic equation, we can complete the square, and we can factor. So we can use a lot of formulas to solve for this. So again, for me, I'm going to use the easiest concept, which is factoring. So I'm going to factor x squared minus x minus 6, which is going to give me x minus 3 times x plus 2. And I can use my zero property to solve for this. And my zero property says this, that when I have two numbers that are being multiplied together and my answer is 0, the only way I can get 0 is if one of these two numbers is 0, because 0 times anything will always give me 0. So hopefully it's easy to see that the only way that I can get 0 from x here is if x is 3, and here the only way that I can get 0 from the x plus 2 is if x would be a negative 2. And if, again, if you don't see it, you can solve algebraically and you get your two answers, right? So the two answers that would give me this would be 3 and negative 2, but you always want to check your work, okay? You always want to verify that you got those answers right, okay? Now, let's see here. All right, let's do these other two examples, move on. All right, so let's do A here. Again, it's telling us to solve algebraically first and then approximate our answers if appropriately, okay? So on this particular problem, before I can use my one-to-one property, I need to isolate the exponent base, yes? So you see I have a 5 that is being multiplied to this base 3 exponent. So to isolate it, what I'm going to do first is I'm going to divide by 5 on both sides. Okay, so I'm going to divide by 5 on both sides. So 5 divided by 5 is 1, leaving me with just with a 3x2 equals 2. 20 divided by 5 is equal to 4. Okay, now if you notice on this one here, I cannot make the 4 have a base 3. So what I'm going to do is I'm going to use my inverse properties, or what and that's actually what I'm going to do to solve for this one. So for this one, what I'm going to do is I'm going to multiply by the natural log of both sides in order to use my inverse property. So when I do this, I have the natural log of 3 to the x is equal to the natural log of 4. I'm going to use my power rule for exponents, and this is going to give me x times the natural log of 3 is equal to the natural log of 4. So to solve for x, I'm just going to divide by natural log of 3 on both sides. And when I do that, I get x is equal to natural log of 4 and natural log of 3. Now, again, just to remind everyone, this is the algebraic answer. So if your homework or on your test, it asks you to answer algebraically, do not use a calculator, give the exact answer, this is what the computer wants to see, or this is what the answer needs to be on your exam. Now, if it says on this particular one, it also says to approximate. We're doing both of them. It says also approximate your result. Then that means to use a calculator. I'm going to plug it into my calculator. I'm going to do natural log of 4 divided by natural log of 3. And it says to round to 3 decimal places. So my answer is going to be 1.262. Okay. All right, let's do B now. Okay, so for B, I need to isolate again the exponent part. So I have a minus 9 there that is being subtracted to the exponent. It gets easy to simplify. I'm just going to add 9 on both sides. Okay, so when I add 9 on both sides, I get e to the x is equal to 27. All right, I'm going to use my inverse property again to solve for x. So I'm going to multiply the natural log of both sides. And again, why is it that I'm using my inverse property? Because it's allowing me to bring that exponent down to something that I can solve algebraically. Okay, so when I do the natural log of both sides, I use my power rule, which is what I'm talking about. My power rule says that I multiply the x to the natural e, but I discovered that the natural log of e is our inverses of each other. That gives me 1. So 1 times x is x. So the right side is just a natural log of 27. So this is the algebraic answer, and the estimated answer or the approximation answer is plugging in natural log of 45 into my calculator, which gives me x is approximately 3.807. And again, it's approximation because I am rounding, okay? Exact answers are the algebraic answers, okay? All right, so let's do this one. Natural log of x is equal to the natural log of 4. All right, so on this particular one, what I can do again is my inverse property for logs. I'm going to take the log of base e to the x, and what I'm going to do is I have to do the same thing. Or another way for you to see it is what I'm going to do is I converted this natural log into the log of base e, and then I'm going to use my my inverse or converting from log to exponent. So again, my base e for this log becomes the base of the exponent. The output of the log is the input of the exponent, and the input of the log is the answer of the exponent. So now it's easy to see that all I have to do is use my calculator to value e to the negative 4, and it's going to give me the value of x. And again, when I plug it into my calculator, rounding to just 3 decimal places, it gives me 0.018. Okay. All right, let's do these couple more. Let's do A. A is 2.8 is equal to the natural log of 3x. Okay. So for this one, I'm going to do the same thing that I just did before. I'm going to convert this into its exponential form. Okay, so to see it, okay, I do this extra step, converting it to the one that shows you the base, so you can see the base. Now I don't have to do this, but again, I like to show you this step. There's other ways to do it, but I'm going to do it this way. Okay, so the first thing I convert the natural log to the natural log of base e of 3 to the x. Then I'm going to convert it to its exponential representation, right? So here, the base of e is e, so that's my exponent. The output of the log is the input of the exponent, so it's e to the 2.8. The input of the log, which is 3x, is the answer of the exponent, which is 3x. Okay, so I just need to solve for x, so I need to isolate the x, so I'm going to divide by 3 on both sides. So the algebraic answer for x is e to the 2.8 divided by 3. Now the approximation, let's put that into our calculator. So I'll do e to the 2.8 divided by 3, and it's going to give me 5.482. Okay, all right, let's do b. So So to do b first, again, I need to isolate the log. So the first thing I'm going to do is I'm going to subtract 5 on both sides. So I have minus 5 natural log of x and subtract 11 minus 5. This is going to give me 6. Okay, I still need to isolate the log. So the next thing I'm going to do is I'm going to divide by a negative 5 on both sides. So I have the natural log of x is equal to 6 over negative 5. Then I'm going to use my inverse property to or to change the exponential in form. Okay, I'm going to change it again. So again, make the log of base e to the x is equal to 6 over negative 5. Change this to its equivalent exponential form. So this is e to the negative 6 to the 5 is equal to x. This is the algebraic answer. Put this into my calculator, and it's going to give me 0.301 is an approximation to x. Okay. All right. All right. So I have 10 minutes. So I'll go through some of these fairly quickly because they're more of the same. Okay. So for the A, to solve for this, before I can solve for the log, I want to isolate the log, and I can isolate it by applying my quotient property. I have two logs. I'm going to condense it to one. Okay, so this becomes the natural log of x divided by x plus 6 is equal to 7. Okay, now if you can see, I'm going to do the same ways that I solved all the others, the previous one. I'm going to change it to its exponential form, and by me doing this, it allows me to simplify my x. Okay, so on here, to solve for this one, I need to solve for x, so I'm going to multiply x plus 6 on both sides. So I'm going to distribute that e to the 7 to both of this. Okay, so once I distribute, I have e to the 7x plus e to the 7 equals to x. I want to put all my x's together, so I'm going to subtract, or I'm going to move everything that has an x to the left, anything that does not have an x to the right. So what I'm going to do here is isolate everything that has the x. So again, my process is this. I am going to subtract x on both sides. This gives me minus x. I'm going to subtract the e to the 7 to the 6 on both sides. So you see this is just a number, but I have two instances of x. How do I isolate the x here on the left side? So to do that, I'm going to factor out an x, okay? So I'm going to factor out an x. This is just going to give me e to the 7th minus 1 is equal to this number here. So to solve for x, I just need to divide both sides by e to the 7 minus 1. And that's going to give me my algebraic answer. X is equal to negative e to the 7 to the 6 divided by e to the 7 minus 1. To evaluate, I just have to put this into my calculator, which will give me my answer. Okay. Um, the second one here, okay, we always want to check our solutions, but here on the right side, what I would do first, again, you can use your quotient property to condense this, okay. Oh, and what they're talking about on this one here, I'm sorry, I'm just going through it quickly. But you saw that my answer was negative. We cannot put negative answers in the logs, okay? So on this particular problem, um, if I would put, since I have a single value for x and the answer is negative here, um, my answer would be no solution because I cannot have negative numbers for exponents. My calculator would give me an error on that particular one. Okay. All right. So let's solve this second one. The first thing that I'm going to do is I'm going to condense the right side by using my quotient property. So I have natural log of x plus 9 is equal to the natural log of x minus 6 divided by x plus 6. So for this one, since I have two logs that are being equal to each other, what I'm going to use is my one-to-one property now. And for this to be equal, the inputs have to be equal, right? So I'm just going to set the input values equal to each other. I have x plus 9 is equal to x minus 6 over x plus 6. Okay, I'm going to do the same thing that I had done on the left side here. I'm going to multiply by x plus 6 on both sides. Okay, this is a FOIL on the right side. Go ahead and do that. Simplify by distributing or doing the FOIL. Condense my equation by combining my like terms. Now, since I see I have a quadratic, I'm going to move everything on one side. So I'm going to subtract x on both sides, add 6 on both sides. Okay. I have this. I have x squared plus 14x is equal to 60, plus 60 equal to 0. Okay. So what I can do is, again, um, I'm going to practice this one since I can't easily factor it. I am going to use my quadratic equation. And I know Ms. Chuka says this all the time. You know, if you have a hard time factoring, if you spend 1 or 2 minutes and you can't factor it, more than likely it's a complex number, or it's something that has no solution, and that's precisely this one. Since this one was hard to factor, when we use our quadratic equation, we saw that we get a complex number, but in this problem they don't want answers in complex form, so we can just answer this one as a no solution. Okay, all right, so let's do this. I think this might be my last example here. Solve for this log. Have a log of base 9 of x minus log of base 9 of x minus 8 is equal to 1/2. So the first thing that I can do is I can condense my left side by applying the quotient property. And this is going to be multiplied the two inputs. So I have log of base 9 of x to the x minus 8 to the 1/2. And what I'm going to do is I'm going to change this into its exponential form. The base of this log was 9, so that's the base of my exponent. The output of the log is the input of the exponent, so it's that to the 1/2, and the input of the log is the output of the exponent. It's the answer, right? So I have this. So I can rewrite the 1/2 as a algebraic uh, problem. That's nine. Nine is 9 to the 1/2. Oh, my clicker wasn't working. Excuse me. There we go. Now it's working. I have 9 to the square root of 9, right? So I can evaluate that. The square root of 9 is plus or minus 3. So to solve for x, I'm going to multiply an x minus 8 to both sides. Again, I'm going to have two answers, one with the plus 3 and one with the minus 3. And when I solve that algebraically, I have a 12 and 6. Again, you always want to check your answers. Put these values back in. If any of those values give you a negative value for the input, it's a no solution. So again, if I input these, so again, um, if I input these, and now I'm glad I checked. If I see if I put 12 here, there's no problem. Log of base 12, log of 12 minus 8 is a positive 4, so this is not our problem. So one of my solutions is 12. But if you see here, if I use 6, log of base 6, but if I plug it into this other one, 6 minus 8, this is going to give me negative 2. This one's going to give me an error. So on this particular one, I do not have two answers. I only have one answer, and my only one answer is that x equals 12. Okay, so again, I want to thank all of you guys for joining me. You have your exam 3 next week. So again, hopefully is preparing you for your exam. Wish you the best of luck. Now I'll pass it back to my presenters. Thank you again for joining me today.
Thank you so much, Mr. Carizales, for this wonderful presentation. If you would like to download a copy of the presentation, you can go up to the top right-hand corner and click on the box with the arrow going down while the presentation is on the screen. We do want to remind you about all our previously recorded sessions, which are available on YouTube on the El Tejano Virtual Events playlist. This session will also be available later on today. Also linked is a short survey to help us improve our Tejano virtual event sessions. Please take a few moments to fill out that survey. Before you all leave, I want to share the Tejano virtual events flyer with the sessions that we will have next week. At 1 p.m. today, we will have When I Grow Up, I Want to Be a Writer by EPCC alumni author Isela Griels. We will be back on with Happy Math Hour next week, and at 11, where in Math 1314 we will cover linear and nonlinear systems, and Math 1324 we will cover the exam third review. Our 1 p.m. session next week, we will cover the career and transfer services. Thank you for coming today. We hope that you all have a lovely weekend. If you have any questions, please feel free to use the chat on our mic, and we hope to see everyone again for Happy Math Hour next week.